Welcome. In this video, I'm going to discuss Kirchhoff's rules. I will state the rules. I will explain them in this video. Then in a later video, we'll talk about how we applied them. There are two rules that are very important for analyzing circuits. Okay, we'll start with the loop rule. And that is that the sum of voltage changes around a circuit loop is 0. I did not say the sum of the voltages around a circuit loop is 0, but the sum of the voltage changes around a circuit loop is 0. And there's a statement of the rule. The first character that you see is the Greek letter sigma. It's a capital sigma. The Greek letter S stands for summation. That first character is sigma for summation, and underneath it is written loop. It means sum the thing that follows over the whole loop. What is the loop? Well, the loop is going to be the circuit. Circuit is from a Latin word which means to go around. A circuit goes around, so we're going to go around this loop. We go around the circuit loop. What is it going to sum? We're going to sum those delta V's. At every point in the loop, if we encounter a change in voltage, a change in potential, we'll put that change into our sum. And after we go around the entire loop, meaning we come back to the point where we started, we add up all those changes, it will sum to 0. Now, I gave an example of this in an earlier video where I talked about a simple circuit, a DC circuit with a battery and a resistor. So an increment of charge would pass through the battery, go to a higher potential, gains potential energy. It comes to the resistor, drops to a lower potential, loses energy, and the resistor is heat. And I said when the charge goes around the circuit, gaining potential, losing potential, when it comes back to the point where it started, I said it has to be at the same potential. Therefore, whatever it gained in the battery, it lost in the resistor. You can go to the lab. You can set up as many circuits as you like with DC power supplies, with batteries, with resistors. Take a multimeter, measure the voltage around the loop, and you'll see this rule is obeyed extremely well. I gave the analogy of it's as though you are in a building, you take an elevator, you go up, walk down the hallway level, go down the stairway to the floor where you started, come back level to the point where you started, you're at the same height. Voltage or potential is similar to a height. Now, I want to point out a little subtlety here. Subtlety are a little thing to be aware of. You might ask yourself, could there ever be an exception to the Kirchhoff loop rule? Well, I will tell you. You'll see in later videos, later topics, you have a changing magnetic field. You can get some interesting things happening in a current loop. But for now, we're not going to have any changing magnetic fields. So as long as that's off the table, this rule is perfectly fine. It's rock solid. We'll work with it. Okay, here's the next rule, the junction rule. The current entering a junction equals the current leaving it. And write it as simply I in, the current in, equals I out, the current out. So what does he mean by a junction? Really, a junction is any point in a circuit. I'll give some examples in this video, but really a junction, it could mean a place where things are joined together, or just, you'll see later. I guess that's the meaning of the word junction. Things come together. A point where something comes together, and the current that goes in equals the current that comes out. Now, why is this rule true? Remember, current is the flow of charge. You can't have charge flowing into an object and not coming out. Why? Because electrical forces are so great, there'd be too much repulsion if you try to pile a lot of negative or positive charge into a point. It would flow out. And likewise, there's no way to create charge, so you can't have more coming out than goes in. It's like water flowing into a pipe. Goes in, it's going to come out. As long as it's in the pipe, the pipe's not leaking, you're not going to lose any of the flow. These are the two rules. Let's talk about, explain how we are going to apply these rules. We'll apply them in a later video. It's going to be very important that we're careful in defining these voltage changes. We're often going to be talking about batteries or power supplies and resistors. When we're summing a set of objects and they sum to zero, they're only going to sum to zero if some are positive and some are negative. Unless all of them are zero to start with. But assuming some are positive, there have to be some that are negative. And it is oh so important to keep track of how we measure these changes to know when it's positive, when it's negative. Typically, in applying the Kirchhoff loop rule, I'm going to talk about two things. The flow of a current through a circuit, and then an imaginary path where you walk around the circuit. So there's the flow of the current, and then there's this path. And so I've even drawn a stick figure there of an imaginary person walking along a circuit. Arrow shows this person's going from left to right. There's a resistor. There's a potential on the left side of the resistor, and different potential on the other side if a current is flowing through it. Delta V, if you're going from left to right, delta V is going to be the potential at the right minus the potential at the left. In other words, it's the later one, the one you come to later, minus the one where you started. Now, the same resistor, you're walking from right to left. The same resistor, but delta V is going to change sign, because now it's V left minus V right. This is oh so important in applying this rule, that you have to consider this kind of imaginary path where you walk around the loop, you walk around the circuit, and you pass over a resistor. The change, you go from one side to the other side. You see on the left side, it's V right minus V left. In the right-hand picture, going the other way, it's V left minus V right. Very important in how we apply this rule. Here's another thing. Oh, so important. The sign of the voltage change for a resistor. The key is you have to remember, since we treat current as positive, current flows downhill. It flows from high to low. If you see a river, a stream, whatever, some stream of water flowing along, you know it is flowing downhill. You don't have to ask which way is uphill, which way is downhill. If you see a river flowing, it's going to be flowing downhill. The same with electrical current. We're talking about direct current. We're not talking about alternating current. We're talking about direct current. It's going to flow downhill. So if current goes through a resistor, it must be going from high to low. Therefore, here you are, you're walking along from left to right, and you notice you're walking the same direction the current is flowing. Current flows downhill. Therefore, you must be walking downhill. Therefore, the change when you go from left to right, we said delta V will be V right minus V left, will be negative. You're walking with the current. It means you're going from high to low. So the change, the later minus the earlier, is negative because you go from a higher to a lower point. Is it always true? Well, the current is going to flow depending upon how the circuit is arranged. But you're free to walk whichever way you want to. Now, when I say walk, it's just your perspective and how you analyze the circuit. So if you happen to be looking at a circuit like it, you might say, well, I'll always go from left to right. That's not an option. If you're going around a loop, go across the top, the bottom, you're kind of circling around. You're not always going from left to right. So on the right-hand side, you're walking from right to left. But the current's going from left to right. You're going against the current. If you were swimming against a river, we'd say you're swimming upstream. Why do we say upstream? Because river flows downhill. So if you're going against the flow, you must be swimming uphill, upstream. So if you're going against the current, that means you're going from a lower to a higher point. Your delta V, the later minus where you started, V left minus V right, will be a positive number. Now, when we calculate these voltage changes, we'll use Ohm's law, delta VI times R. But what we're going to find out is now we have to use a positive or negative sign when we apply that law. Now let's consider the sign of the voltage change for a battery. When I say battery, it could be a DC power supply. They behave the same way. It's just kind of simpler to say battery. The battery or the DC power supply has a low side and a high side. Here we see the symbol. We have the low side as the shorter bar and often marked with a negative sign. The high side has a longer bar marked with a positive sign. Sometimes the positive and negative may not be there. It's a little bit optional. But you can tell which is the high side, which is the low side. Remember, it doesn't necessarily mean positive and negative. It means high and low. So if you are in a circuit, or your perspective as you go through the circuit, you're following a path from left to right. You're going from the low side to the high side. You're going from a low potential to a high potential. Therefore, your delta V is greater than 0. If I told you that you were going from the low side to the high side of a 12-volt battery, your delta V would be plus 12 volts. Now, what if you have the same battery, the same high side, same low side, but you're going the other direction? You're going from right to left. You're stepping, so to speak, from the high side to the low side. Therefore, your delta V is less than 0. It's going down. Again, if that's a 12-volt battery, you go from the high to the low. your delta V would be minus 12 volts. Now you may think, I'm not going to confuse things. I'll always go from the low to the high. Not an option. We're going to have circuits that will have multiple power sources in them, multiple resistors in them. Maybe the power supplies, batteries may be oriented in different ways. So when you do this loop around the circuit, you'll find that some of them you may cross from low to high, some you may cross from high to low. It's not an option to always go from the low to the high. You have to be prepared to treat it in whichever way you're crossing the battery. Okay, now for the junction rule. You say, what's the junction? Well, I like to use this example, even though you might not normally think of a resistor as a junction. I like to use this example. The current going into the resistor equals the current coming out, just a single resistor. I like to point this out because we often speak of a resistor restricting the current in a circuit. And I don't want you to think, if I make a statement like the resistor limits the current or restricts the current, there might be a temptation to think that more current goes in and less current comes out. That would not be true. Even though the resistor affects the current in the circuit, that have the same current throughout the circuit, assuming it's one loop. So the current flows in. You cannot have charge building up in the resistor. You cannot have charge disappearing. Whatever flows in must come out, just like water going into a pipe. This is kind of a more traditional view of a junction. Junction meaning where multiple things come together. Here you have, some consider these black lines, wires kind of coming from left to right. You come to a point where this one wire splits into 3 wires. If this was, this could be a water outlet. Think about how a water outlet, you could have a water outlet on the side of the house, and you have some kind of attachment there that it breaks it into 3 branches, and water can go to 3 different hoses, for instance. It's my analogy with the current. The point is, what goes in must come out. You have a current flowing in. It splits into 3 branches, I1, I2, I3. So the current coming out of that black dot, so to speak, just means the point where they're joined together, is the sum of 1 plus 2 plus 3, the 3 currents. The junction rule says you cannot have charge building up. You cannot have charge being created. Therefore, IN equals I out. IN equals I1 plus I2 plus I3. Okay, that's introduction to the 2 Kirchhoff rules. The loop rule for summing voltages, the junction rule for comparing the current in, the current out. Later video, we'll talk about the applications. Again, these are 2 very important rules for analyzing circuits. That's the end of the video. Thank you for watching all the way to the end.